All right, welcome to day 2 of our computer science journey. Today, we are digging into the absolute foundation of everything computers do, Boolean algebra. Let's get right into it.
I mean, seriously, think about that for a second. It's kind of wild. Every single thing your computer does, from running the most advanced AI model to you just browsing the web, it all boils down to 3 super simple ideas: and, or, and not. This is literally the language computers use to think, and we're about to become fluent.
So what exactly is this stuff? Well, it's a mathematical system that a guy named George Boole cooked up way back in 1854. And for decades, it was mostly just an academic curiosity. But then, in 1937, this brilliant engineer named Claude Shannon had a light bulb moment. He realized you could apply these true-false rules to electronic circuits, and that single insight created the mathematical backbone for every digital device we have today.
At its heart, Boolean logic gives a computer its entire vocabulary. And get this, it's a vocabulary of just 3 words. Let's break down each one.
First up is the AND operation, which you'll often see written with a dot. Think of it as the strict bouncer at the door of logic. It's incredibly strict, and its rule is very simple.
Yeah, the AND operation is pretty demanding. Looking at its truth table, you can see that the only way to get a true output, a 1, is if input A and input B are both true. If even one of them is false, the whole result is false.
And this is a perfect way to picture it. Imagine 2 light switches controlling one bulb, wired one after the other. If only one is on, the circuit is still broken. You need both to be flipped for the light to turn on. That's AND.
Now, let's move to the second word in our computer's vocabulary, the OR operation, usually shown with a plus sign. This one is a lot more forgiving.
The OR operation gives a true output if input A or input B is true. The only way to get a false output is if both inputs are false. As long as at least one input is a 1, the result is 1.
The perfect analogy here is wiring those same 2 switches in parallel. Now, the electricity has 2 paths it can take to the bulb. As long as one of those paths is closed, meaning one switch is on, the light will work.
And finally, the simplest operation of all, NOT, represented by a little apostrophe. It's also called the inverter, and it does exactly what its name suggests. It takes a single input and just flips it. If you give it a 0, it gives you back a 1. If you give it a 1, you get a 0. Simple as that.
Okay, so we have our 3 basic operations. But to do anything useful with them, we need a set of rules, or laws, that let us manipulate and simplify complex logical statements.
Some of these are really clever. The identity law says adding a 0 or multiplying by a 1 doesn't change anything. The null law shows that ORing anything with true always results in true. The complement law is neat. A value or its opposite is always true. But the real powerhouse here is De Morgan's theorem. It gives us a clever way to handle when we need to invert a combined AND or statement. It's a critical tool for simplifying complex circuits, as we'll see later.
And the good news is, you already know many of these rules intuitively. The commutative law, which says A plus B is the same as B plus A, and the distributive law work just like the algebra you're used to. So you're already halfway there.
So far, this has all been abstract math. But here's where it gets truly amazing. This is the moment where these ideas leap off the page and become physical things inside your computer.
Each of those operations we just discussed, and, or, and not, has a physical counterpart called a logic gate. These are tiny electronic circuits built from transistors, and they are the fundamental building blocks of all digital hardware. The goal of good design is to solve problems using as few of them as possible.
In circuit diagrams, they each have unique shape. The AND gate looks like a D. The OR gate has a curved side, and the NOT gate is a triangle with a little bubble. What's amazing is the concept of universal gates, like NAND and NOR. It means you can build every other type of logic gate using just one type. For example, a whole processor could be built just out of NAND gates. This simplifies the manufacturing process immensely.
All right, let's see how this all comes together in the real world. Where do you actually encounter Boolean logic every day?
It's everywhere. In programming, an if statement is pure Boolean logic. When you use a search engine, you're using it to filter results. Even your car's safety system runs on it. The engine will only start if the key is detected and the seatbelt is buckled. And at the lowest level, your computer's CPU is just billions of these tiny switches, all working together based on these simple rules.
So the crucial point is this. Why did we learn all those laws?
Because they allow us to do something incredibly important, make our digital circuits more efficient.
Let's walk through an example. We have the expression F equals A and B, or A and not B. Step 1. Using the distributive law, we factor out the common A. That leaves us with A and the quantity B or not B. Step 2. We apply the complement law. We know that any value ORed with its opposite is always true, or 1. So our expression becomes A and 1. Step 3. The identity law tells us that anything ANDed with 1 is just itself. So our final result is F equals A.
Look at that! We took a complicated expression that would have required multiple logic gates to build, and by applying our rules, we proved it's equivalent to just a single wire carrying the value of A.
And why does this matter? Because simplifying a circuit means using fewer components. Fewer components mean the chip is smaller, uses less power, generates less heat, and runs faster. This process of simplification is at the very heart of how we design more powerful and efficient computers.
So we end on this thought. Our entire incredibly complex digital world is built upon just 3 simple operations and a handful of rules. If you can master these fundamentals, what could you create?